Wow, it has been a while. Long story short, I got wrapped up studying for the midterm last week, and I did record a video yesterday, but the file got corrupted, which wasted around an hour of footage, and that was annoying. But it still got me to study. But, as always, complaining will need to wait, because I have a whole heck of a lot of statics to go over tonight. In fact, I have been neglecting my statics studying so much that tonight is going to be dedicated entirely to statics. With that, let us begin. Okay, first of all, let's say that we have some area, like so. And there is a force that is distributed over this area. Like we put a bunch of sand on top of it or something. Using the methods that we've been taught so far, what we would need to do is we would need to calculate the weight force and moments of every single grain of sand on this thing and add them all together using force couple systems. And then we would get the, effect that huge pile of sand would have on this plate. But, as I'm sure all of you already realize, this is extremely impractical. But what we can do is we can simplify the effect of that sort of bank of sand into a single weight force acting at the center of mass. The centroid, if you will. Here's how it works. For the sake of simplification, let's say that we only have three forces acting on this thing. Weight force 1 at point 1, weight force 2 at point 2, and weight force 3 at point 3. We can simplify this down. A single weight force acts at the point x bar, y bar. X bar and y bar are both called the first moment of area. We can find a first moment of area with respect to x and a first moment of area with respect to y. The sum of the first moments with respect to x is going to equal x bar times that force w, or it is going to equal the sum of all the x's times the delta w's. The delta w's are just w1, w2, and w3, which were our separate weight forces at different points that I erased before I drew this. The sum of the first moments with respect to x is also going to be equal to the integral of x dw. We use much the same logic to find the sum of the first moments with respect to y. Now let's say that we have the same situation as before, except instead of that, plate, we have a wire. We have multiple weights acting at multiple places, and they can be condensed down to one force acting at the centroid being at x bar, y bar. We can find both elements of the first moments using the same equations that we used before. Okay, I need to be going faster than this. It's gonna be worth studying, but I need to get through this. There's a quiz tomorrow. Okay, we have this little plate, this 2D plate right here. The first moment with respect to y, which we signify as q sub y, is going to be x bar times a being the area of this plate thing here, which is also going to be equal to the integral of x times dA. The first moment with respect to x is going to be y bar times a, or the integral of y times dA. When calculating first moments, it is important to realize that the variable that you are taking the first moment with respect to is the variable that you will not use in the equation. When calculating with respect to x, we use y bar. When calculating with respect to y, we use x bar. Let us now instead say that we have some line. The equations for the first moments are going to be the same, except instead of a, we have L, which is the length of the line, and instead of dA, we have dL. Next, let's imagine that we have this funny looking shape right here. We know that we can divide this shape up into more, less funny looking shapes. Let's call them G1, G2, and G3. We will also call the entire shape G. The sum of the weight forces acting on all these plates separately is the same as if they were all part of the same plate. The same can be said about the relationships between the centroids and the areas, meaning that if we find the centroids for all of these plates individually and then add them together, we are going to get the centroid for the plate as a whole. It is also important to note that there is a sheet of x bar and y bars. It's going to be something that'll be good for me to print out when this inevitably appears on the midterm. But that's not something that I'm worried about right now. This is what cramming looks like for me. It feels like that the work keeps just piling up, and I don't have enough time to do all of it. I mean, to study for last week's midterm, I basically neglected statics for the entire week. That was not a good idea, but I don't know how else I would have done it. Okay, I'm just gonna keep going, get through all that I can tonight. To recap, what we've learned here is the first moment with respect to x is x bar times a, or the integral of x times dA. The first moment with respect to y is x bar times a, or the integral of x times dA. We also know that if we have some sort of composite plate, we can divide that plate up into separate shapes, find each of those shapes, x bars and y bars, and all their first moments, and then use that to find the first moments and x bar and y bar for the entire shape. But we can solve for x bar and y bar by using integration. We want to find x bar times a, which is, of course, the first moment with respect to y. I keep saying that because I want to remember it. Let us say that we are given this strange shape. We're going to draw on some things from physics and from calculus. We make an infinitesimally thin vertical strip here. Using these two little things, we can figure out... Okay, there's something that I missed here. This is correct. dA is equal to y times dx. Instead of putting the integral of x times dA, we are going to put the integral of xel times dA. Bear with me here. Every single one of these rectangles that we take as we integrate are going to have their own centroid. And remember, we can add up all the centroids of all the infinitesimally small rectangles to find the centroid of this object. And that's what we're doing. So xel is going to be the x component of the centroid for this particular rectangle. In this case, our integration is set up in such a way that xel is simply x. But that may not always be the case. X bar a is finally going to be the integral of x times y times dx. We can also find the first moment with respect to x, y bar times a, using much the same method. Except this time, yel is not just y, it is y over 2. I had to change rooms, no time to explain. This one's a little more echoey. Hello? Where was I? Oh yeah, y bar el. In this specific case, since we have these rectangles, y bar el is going to simply be y over 2. Meaning that the first moment with respect to x is going to be equal to the integral of y over 2 times y times dx. Notice that we have dx here. If we set this integral's bounds from a to b, a is right here where the shape intersects the x-axis, and b is right here, right below the end of the shape. If we wanted to find x bar and y bar, the coordinates of the centroid, then we would simply divide the first moment by the area, like so. This would give us the coordinates of the centroid. Oh my god, this marker is so acrid. I can feel my brain cells dissolving in the fumes. But I can actually see this marker. Plus, I'm pretty sure I won't feel the effects of any permanent brain damage until I'm at least 35. Which is years away. So let's continue. Next, let's say that we're given this length L. We want to revolve this length L around the x-axis in order to get some surface of revolution. Like so. How are we going to find the area of this surface of revolution? Well, I'm glad you asked. It's going to be equal to 2 pi times y bar times L. We know this line is going to have a centroid, and that this centroid is going to have some coordinates x bar comma y bar. Meaning if we find the centroid, and we find the product of the y component of the centroid and 2 pi and L, we are going to get the area that results from us revolving this shape around the x-axis. Let us now instead say that we are given an area, and we want to revolve this area around the x-axis to get a volume. What is going to be the volume of this volume? Pretty similar, except volume is going to be equal to 2 pi y bar times the area. This area that we're given has some centroid, and we can use the y component of this centroid to find the volume. Next, let's say that we're given a beam, and on top of this beam is placed a non-uniform load. To show this load, we plot it against the beam in terms of weight per unit length, meaning that we can draw this non-uniform load like this. Note here that this hump thing does not represent volume. This is not a physical object that is being placed on top of the beam. It is a representation of how dense the weight is at certain points along the beam. So we know that the weight, for example, here is going to be denser than the weight here. But if we reach back a little bit, we know that this can be just condensed down to a single weight acting at the centroid of this volume. It is not the centroid of this. It is the centroid of this, where weight is equal to x dw, dw being the change in the density of the weight, while the first moment with respect to y is going to be equal to x bar times a, or equal to the integral of x times dA. We can divide this by the area underneath this curve in order to find our x bar. We find y bar much the same way. For bodies in 3 dimensions, it actually doesn't get much more complicated. X bar times the weight force of the object is going to be equal to the sum of all the x's times all the delta w's, or the integral of x times dw. Same thing for y bar times w, except now we have a z bar times w. Z bar being, of course, the z coordinate for the centroid. Alright, that was good. I'm glad I powered through that. That was really hard, but I think it'll be worth it for the quiz tomorrow. I'm still nervous because I haven't gone over second moment of inertia, which are a little bit more complicated than a topic which is a little bit more complicated than the stuff I've gone over tonight, but I do have faith that I will be able to get through it. So it's been a night of good progress. So wherever you are, whatever time it is, I hope you all have a fantastic evening. We're nearly to spring break, and with that, I'll see y'all tomorrow.